All right, let's talk about one of the most famous charts in all of science, the periodic table. You've definitely seen it hanging in a classroom, but it is so much more than that. It's basically the key to understanding, well, everything. But let's be honest, have you ever really looked at it and wondered, why is it shaped like that? All those gaps and weird blocks sticking out, it just looks kind of strange, right? Well, it turns out that shape isn't random at all. It's hiding a fantastic story about how the universe is put together. So I want you to stop thinking of it as a chart and start thinking of it as a secret map. Every single position, every column, even those weird gaps, are clues that tell us exactly how matter is built, from the simplest atom to the most complex stuff in the universe. So, what's the big secret? What's the key to this map? It all boils down to one thing: electrons. And not just any electrons. We're talking about the ones on the absolute outermost edge of an atom. These are the frontline soldiers, the ones that do all the work and are responsible for basically all of chemistry. And this is where that weird shape starts to make perfect sense. It's not arbitrary at all. It's grouped into these blocks. You see them here as S, P, D, and F. Each block is like a neighborhood, and it tells you what kind of path that element's most important, most reactive electron is on. This is the first layer of the code we're about to crack. Okay, so if we're going to read this map, we need to crack the electron code. And to do that, we need to understand the rules for how electrons actually arrange themselves inside an atom. Now, the technical term for this is electron configuration. But really, all that means is the specific address of every electron. The easiest way to picture it is like an onion. Electrons fill up these layers or shells, starting from the very center and working their way out. And this diagram, this is our decoder ring. It looks a little complicated, but it's super simple. It shows us the exact order that those onion layers get filled. You just follow the arrows. You start at the top with 1s, then you go to 2s, then 2p, then 3s, and you just keep following the path. This is the universal rulebook for building any atom. So what happens when you follow those rules for the elements way over on the far right side of the table? You get the noble gases. And what makes them so special? Well, their outermost shell of electrons is completely, totally full. This makes them unbelievably stable. They don't want to react with anything. They've reached a kind of chemical perfection. And every other atom on the table wants to be just like them. And that desire, that need to get a full outer shell just like a noble gas, that's the engine that drives all of chemistry. It's why atoms connect with each other in the first place. They form bonds by sharing, stealing, or giving away electrons, all in a desperate attempt to get that stable, perfect configuration. To make this easier to see, a chemist named G.N. Lewis came up with a totally brilliant and simple system. You just write the element symbol and you draw dots around it for each of its outer electrons. And here's the magic part. The number of single, unpaired dots tells you exactly how many bonds that atom wants to form. Look at carbon. 4 single dots, it wants to make 4 bonds. It's so simple, but it's incredibly powerful. And here it is in action. You've got hydrogen with its one lonely electron, and fluorine, which also has one lonely electron. So what do? They make a deal. They share those 2 electrons so that now they each feel like they have a full outer shell. And that shared pair of electrons right in the middle, that is the chemical bond. That's the glue holding them together. This whole motivation has a name. It's called the octet rule. Octet just means 8. For most atoms, the magic number is 8 outer electrons. They will do whatever it takes, share 1, 2, even 3 pairs of electrons to get that stable set of 8, just like their favorite noble gas. This is the #1 rule of the game in chemistry. Okay, so we've cracked the code for how atoms bond. But now I have to let you in on a little secret. All these flat drawings we've been looking at on the screen, they're a lie. A useful lie, but still a lie. Because molecules don't exist in 2D. They're 3-dimensional. And this slide shows you exactly what I mean. On the left, that's the flat Lewis structure for methane, CH4. It looks like a plus sign. But that's not what methane actually looks like. The reality is on the right. It has a very specific 3D shape called a tetrahedron, where those hydrogen atoms are spread out as far away from each other as they can possibly get. So what forces it into that shape? It's an idea with a long name, but a beautifully simple concept: VSEPR theory. It stands for valence shell electron pair repulsion, and it means exactly what it sounds like. All those electron pairs around the central atom are negatively charged, so they repel each other. They push each other away as far as possible, and that pushing is what creates the molecule's final 3D shape. That's it. And what's so cool is that this one simple rule of repulsion lets us predict the shapes of molecules with amazing accuracy. This table just shows a few examples. Depending on how many atoms are attached and how many unshared pairs of electrons are doing the pushing, you can know for sure if the molecule is going to be straight or bent like water or a pyramid or that tetrahedral shape we just saw. It's all predictable. Now, you might be thinking, okay, 3D shapes, I get it. Who cares? Well, it turns out this is maybe the most important part, because a molecule's 3D shape directly controls its properties, how it tastes, how it smells, how it acts in the real world. Shape determines function, period. To understand why, we need one final concept: electronegativity. It's a fancy word, but just think of it as how greedy an atom is for electrons. When two atoms form a bond, it's basically a chemical tug of war over those shared electrons. Some atoms, like fluorine, pull super hard. Others are much weaker. So, when that tug of war is uneven, the electrons end up spending more time around the greedier atom. This creates what we call a polar bond. One end of the bond becomes a little bit negative, that's what the delta minus symbol means, and the other end becomes a little bit positive. You've basically created a tiny microscopic magnet. And this explains so much about the world. Like that old saying from chemistry class, like dissolves like. A molecule's overall polarity, which comes from its 3D shape and all its little bond magnets, determines what it will mix with. Polar molecules, like water, love to dissolve other polar things, but they totally repel nonpolar molecules, like oil. This is why oil and water don't mix. It all comes back to shape and that electron tug of war. Wow. So we started with the shape of the periodic table, and we've seen how it codes for electrons, which dictates 3D molecular shapes, which then dictates how things actually behave. It's all connected. But let's bring it full circle and go back to the map itself. Because here's the thing, the standard periodic table, the one we all know, is just one possible design. It's a human invention, designed to be practical for printing in a textbook. So what if we drew the map of the elements in a totally different way? And people have been doing just that for years. Check these out. You've got the spiral table, which shows how the elements flow continuously without any breaks. There's the curled ribbon table, which is beautiful, but also highlights how important silicon is. And then there's the atomato table, which tries to be a perfect map based purely on the math of electrons. These aren't wrong, they're just different ways of looking at the same deep truths. And that really leaves us with one final kind of amazing thought. The periodic table isn't some fixed law of nature. It's a map. It's a model that we designed to help us understand the world. And if we know that the map can be redrawn to show us new patterns and new connections, it just makes you wonder, what other secrets are out there, just waiting for someone to come along and find a new way to look?